This video covers nonlinearity and shear-dependent viscosity for polymer rheology and processing. I apologize in advance for the quality of this video. When I'm filming from my laptop, it's a little bit worse when I'm filming from my regular computer, so please bear with me. This is video 1 of nonlinearity and shear-dependent viscosity. So the typical linear behavior is for a Newtonian fluid. And for a Newtonian fluid conducted at a constant temperature, the only stress generated is in simple shear flow. And the shear viscosity does not vary with shear rate. So you have a linear relationship. Quite literally, your viscosity remains constant no matter what shear rate you're dealing with, as shown here. For a Newtonian fluid conducted at constant temperature, the viscosity is constant with respect to time of shearing as well. Stress falls to 0 when shearing is stopped. Any future measurement of viscosity produces the same result. Viscosities measured in different types of deformation are proportional, and viscosity measured by uniaxial extensional flow is 3 times that measured in simple shear flow. Any deviation from this definition is considered non-Newtonian. And then you're dealing with different sort of behavior, and you typically are looking at non-linear type of behavior. Viscometers are available to measure the effect of shear rate on viscosity, and many materials that you would deal with in a polymeric situation would depart from this Newtonian behavior. And these include dispersions, emulsions, and of course polymeric solutions. In most, viscosity was found to decrease with an increase in shear rate. And shear thinning is typically what we call that, or pseudoplasticity, or temporary viscosity loss. And so I'm going to describe a number of models, mathematical models, that account for ways to approximate pseudoplasticity. So here you have a typical shear thinning behavior viscosity versus shear stress plot. So here we have viscosity on the y-axis versus shear stress on the x-axis. And you get this type of curve. Here you have a lower Newtonian region where this is constant, and you have an upper Newtonian region where this is constant. In between those two, you have a change in viscosity with shear stress. The lower Newtonian region is also known as zero shear viscosity. And it's important to point out that this lower region is based on the lower shear stress, not viscosity. And here you have the upper Newtonian region, which is based on shear stress, not viscosity. In a plot like this, at very low shear rates and stresses, viscosity is constant. At very high shear rates and stresses, viscosity is constant. These are often referred to as lower and upper Newtonian regions, and for the purpose of your exam, you should know that these are called the lower and upper Newtonian regions, not just lower and upper, as they're shown on the curve. Lower and upper refer to the shear rate, not the viscosity, and the higher constant viscosity is also known as the zero shear viscosity. So here we have, again, a typical curve, where we have the zero shear viscosity and the lower Newtonian region here, and the upper Newtonian region shown here. And a wide range of shear rates are needed to characterize the entire flow curve. So you need to kind of take everything like that into account. One way to do this is to use mathematical models. And here we have the cross equation shown here, or the equivalent cross equation shown down here. In this case, you have viscosity sub-zero and viscosity infinite, and these refer to asymptotic values of viscosity at very low and very high shear rates. K is a constant parameter with time units, and M is a dimensionless constant. And here's an example of the cross equation as applied to certain solutions. So here you have these dots represent the experimental data, and the line actually represents the cross equation. So in this case, you have a zero viscosity of 1.82 Pascal seconds and the infinite viscosity of 2.6 millipascal seconds, and these are the constants that produce this particular cross equation line. And this is for a polyacrylamide solution. Here we have one that is for blood. Again, the dots represent the experimental data, and the solid line represents the cross equation approximated to this. And here you have these variables that fit that particular viscosity versus shear rate behavior. Here we have some other systems. This is an aqueous latex, and again, you have the experimental data represented by the dots, and the cross equation fit to that data using these parameters. And here is a xanthan gum solution. Once again, the dots represent the experimental data, and the cross equation represents the fit of that particular experimental data using these parameters. Oftentimes, the cross equation is modified in a certain way, and one way is the Carreau equation, shown here. These mean similar asymptotic values of viscosity at very low and very high shear rates. K1, in this case, is a constant parameter of time units, and M sub 1 is a dimensionless constant. The Ellis equation, shown here, is a reduction of the cross equation. And this applies for viscosity values that are much, much lower than that asymptotic value, or much, much higher than that infinite value. Again, K is a constant parameter of time units, and M is a dimensionless constant. When you redefine the Ellis model, shown here, it can be written this way. And when you redefine the Ellis model, and to get this equation, it is also known as the power law model, which is used extensively. N is the power law index, and K sub 2 is the consistency. And the units there are Pascal seconds to the N, where N is the power law index. Further, if we have a viscosity that's very, very much lower than viscosity sub 0, we generate this equation, or it can be rewritten as this equation here, which is the Sisko model. So between the cross equation, the power law model, and the Sisko model, we have the ability to approximate a lot of different types of non-linear data. The power law model fits the experimental results for many materials. It's often used to describe non-Newtonian flow properties in theoretical analyses and in practical engineering applications. I use it extensively when doing capillary rheometry. But you do have to be careful in using this model outside of the range of data used to define it. And they all have limitations in that regard. Here is the power law parameters for well-known non-Newtonian materials. So here is your constant, here's your power law index. So once again, here's your power law model. So you have some ballpoint pen ink, fabric conditioner, the polymer melt. You can see that these numbers vary significantly depending on what material you're talking about. Molten chocolate, synovial fluid, or the fluid in your joints, toothpaste, skin cream, and lubricating grease. And again, these vary as well. And the shear rate range has to be specified when you're applying the power law. So again, these are for lower shear rates, these are for much, much lower shear rates, and these are for higher shear rates. So you do have to specify that shear rate range so you know that when you're applying the power law, it is appropriate to the system. One problem with the power law is that it fails at high shear rates. The viscosity approaches a constant value at these rates. But you can rectify this by using the Sisko model instead. So again, this equation here, it being the Sisko model. The Sisko model originally was proposed for high shear measurements of lubricating greases, which is why it's more appropriate at high shear rates, more appropriate than the power law. So again, we have the applicability of the Sisko model to actual experimental data. And so here we have the Sisko model, that is the solid line, and the dots are the experimental data, and as you can see, it fits quite well here in this approximation of fabric softener with viscosity versus shear rate. And here you have a carbopole solution with these parameters fit into this equation being the Sisko model. And it fits this one quite well also. So again, the solid line is the Sisko model and the dots are the experimental data. Here you have a polymer liquid crystal, and looking at the shear rate range is one thing you should kind of take into account. This goes from 10 to the negative 2 to 10 to the 2. This goes from 10 to the 0 to 10 to the 4, so we're covering about 4 orders of magnitude when we're doing this. So again, this is the Sisko model here, and this is the experimental data using these parameters. And here you have yogurt. Again, this is the experimental data, and the solid line is the Sisko model applied to these data. So here is a typical viscosity versus shear rate curve for the same data using the cross equation, the power law, and the Sisko models. So you can see here the dashed line is the cross model, and this goes from below 10 to the negative fifth shear rate to over 10 to the third. So we have 8 orders of magnitude here that this can cover effectively for the cross model. The Sisko model is a little narrower. You can cover about 7 orders of magnitude. And the power law model, while it fits the data very, very well, really only can cover about 2 to 3 orders of magnitude in between. So it's important to make sure that the model that you're choosing can cover the appropriate shear rate range for the data that you're looking at. Also, for the purpose of the exam, I would know this particular figure quite well. Thus concludes video 1 for nonlinearity and shear-dependent viscosity. Thank you.